This video tutorial will cover all the different types of calculations and problems you encounter within this gases and atmosphere chemistry unit. But before we start, let's talk about pressure. Now, pressure is defined as the amount of force exerted per unit area. So what we do is we measure force using newtons, and area is measured in meters squared. If I have 1 newton per meter squared, that is equal to 1 Pascal. A Pascal is symbolized by a capital P and a lowercase a. So what does 1 newton of force feel like? If I place an apple on your arm, the force of this apple pushing against your arm would be approximately 1 newton. That's how much 1 newton would feel like. However, when we deal with pressure, we must not only look at the force component, but also the area component as well. So for instance, let's say I exerted, 5 newtons of force against your arm by, pushing you with my finger. That shouldn't hurt because that would be low pressure because you're not exerting it, you're exerting the force over a large area of my arm. So you're spreading all that force around a large area. So there's not a lot of pressure in this situation. On the other hand, if I exerted 5 newtons of force on your arm using a needle though, so same amount of force in both situations, but instead of spreading it over a large area, I'm concentrating over just one small area now. And because of that, you have high pressure in this system. So high is the pressure that the needle will go through your arm. So make sure you know the difference between the word pressure and the word force. Okay? Pressure depends on force as well as area, whereas force is independent. Although we'll use the Pascal as our primary means of measuring pressure, there are other forms, other units to measure pressure as well. So for instance, you will encounter the atmosphere. You can also encounter the kilopascal. Primarily we'll be measuring kilopascals actually. So the kilopascal is just like, for instance, we can measure distance using meters, but we can also measure distance using kilometers. Well, it's the same thing over here. 1 kilopascal is equal to 1,000 pascals. Finally, you'll also encounter the millimeters of mercury as well as the torricelli. So let's first take a look at the word atmosphere, or the units of atmospheres. What is 1 atmosphere? Well, if you were standing at sea level and it was 0 degrees Celsius outside, well, the amount of pressure exerted by the atmosphere on you at that point would be 1 atmosphere of pressure. And 1 atmosphere of pressure is equivalent to 101.325 kilopascals of pressure. Let's take a look at the millimeters of mercury, or the torricelli. Let's pretend at the same situation, at sea level, at 0 degrees Celsius, I carried with me a bucket full of mercury. And inside this bucket full of mercury, I have a small glass tube. What would happen is the amount of atmospheric pressure, the 1 atmosphere of pressure, would push down on this pool of mercury and force it up into the tube. And what would happen is, if I had this apparatus at sea level at 0 degrees Celsius, it would rise 760 millimeters high, which is why we call it 760 millimeters of Hg, which is the symbol for mercury. Now, to honor the scientist who came up with this method, his name was Torricelli, we don't use this unit anymore, millimeters of mercury. Instead, we call it the torricelli, T-O-R-R. However, depending on the textbook you look at and depending on what type of equipment you're using, some of the older equipment, older textbooks will still mention it as millimeters of mercury. But just so you know, we have stopped using this form and we are now using the torricelli instead. So just to recap, 1 atmosphere of pressure is the same as saying 101.325 kilopascals of pressure, which is also the same as saying 760 millimeters of mercury or 760 torricellis. So how do we convert between these different units? Well, what we need to do is we need to set up our ratios. So for instance, if I have 845 torricellis, how many kilopascals would that be equivalent to? So what we do is we first set up our ratios. I usually like to put whatever I'm looking for, and in this case I'm looking for kilopascals, in the numerator, so on the top part of the fraction. So kilopascals, and since I have torricellis, I put it at the bottom. So it's always what you want over what you've got. That's my personal preference. If your algebra is okay, then do it any way you want. That's fine. If your algebra is kind of weak, then I recommend you stick to this one over here, where you place your unknown value at the top and what you do know at the bottom. Now I have kilopascals and torricellis. And from up here, I know that 101.325 kilopascals is the same as saying 760 torricellis. So I just fill it in over here, 101.325 to 760. On the other side, I'm trying to find out how many kilopascals would 845 torricellis be equivalent to. So at this point, I like to erase this part over here, the rough, and solve for the unknown. So I multiply up over here, 101.325 times 845 divided by 760, and that gives you 112.66 kilopascals, which I can then plug in over here, and I'm done converting. Now, at this point, could you please pause the video and try out these questions over here? I'll give you the original ratios over here, follow the exact same sample, and try and solve for these two problems yourself. Hopefully this is the answer you received or you calculated out. If so, fantastic. Now, when doing future problems in this unit, please be sure to convert to kilopascals from this point on. Very, very, very rarely will the question ever ask you to calculate your final answer in atmospheres or millimeters of mercury or torricellis. Usually they will ask you for the answer in kilopascals. The other reason why I'm asking that you could start to convert to kilopascals always is because one of the equations later on this unit can only use kilopascals. If you do not convert to kilopascals right off the bat, you will get the wrong answer. So the first gas law that we'll be looking at is called Boyles Law, named after Robert Boyle, a scientist who looked at the relationship between pressure of a gas and the volume of a gas. So what he found was, as long as the temperature of the gas remained constant, so as long as the temperature does not change, the pressure is inversely proportional to the volume, meaning that as the pressure increases, the volume decreases. Take a look at this. It just makes sense, right? If I increase the pressure of my gas, the pressure pushed upon my gas, the volume of my gas decreases. If I lessen the pressure, so small pressure, the volume is allowed to increase. So this shows that pressure is inversely proportionate to volume. So inversely proportionate means one goes up, the other one goes down. So if volume increased, well then pressure must decrease. And so this is the proportionality symbol to show that they are inversely proportionate. Now, if you look at a graph of volume versus pressure, over here, notice that my volume is slowly decreasing. So according to Boyle's law, the pressure must increase. Let's take a look at this. Pressure is equivalent to 1 over V. So 1 over 5 is 0.20. 1 over 4 is 0.25. 1 over 3, 0.33. 1 over 2, 0.5. 1 over 1 is 1. Notice how my pressure is slowly increasing, while on the other hand, my volume decreases. And so if you plot a graph of pressure versus the inverse of volume, you get a nice straight line. And if you recall from grade 9, plotting the equation of a line, slope is equal to rise over run. In this case, rise is measured in pressure, and the run, x-axis, is measured in inverse volume. So P divided by 1 over V, if you know how to do your fractions, well, basically we multiply by the inverse, so it's P times V. And if you notice, the slope at this point and the slope of this point are identical because it's a straight line. Thus, the ratio between pressure and inverse volume is identical at any given point. So since the slope at pressure 1 and volume 1 is equal to slope, but slope is the same anywhere on the line, well then, I can also say pressure 2 times volume 2 also equals the same thing. And thus I can have the equation P1 V1 is equal to P2 V2, where if I multiply these ones, they should be the same number as if I multiply it on this side over here, because the slope remains constant. And there we have it, the equation for Boyle's law. Pressure 1 times volume 1 is equal to pressure 2 times volume 2. The next gas law is Charles's law, named after Jacques Charles, a French scientist, who looked at the relationship between temperature and volume, as long as pressure remains constant this time. So this only works when pressure remains constant. And he found that the temperature and the volume of gas have a direct proportionality, meaning that if I increase the temperature of a balloon, so here's my balloon, if I put it over flame anyway, the gases inside will start to move faster. The faster they move, the more force they apply on the balloon, and it causes the balloon to expand larger and larger. And so if I increase temperature, then I will also increase the volume of my gas. So this is a direct proportionality, meaning they both go up at the same time, as opposed to an indirect proportionality, as we saw in Boyles Law, where if I increase the pressure of a balloon, so if I increase the pressure against the balloon, then I must decrease the volume of my balloon. So my balloon decreases in its volume. But anyway, just make sure you know that if I increase the temperature of the balloon, of the gas inside the balloon, the volume of the balloon will increase. And so the equation for Charles's law is V divided by T is equal to V divided by T. So volume of the initial, temperature of the initial, volume final, temperature final. Or if you prefer, V1 over T1 is equal to V2 over T2. Either or would be fine. Now we're looking at Gay-Lussac's law, another French scientist, and he described the relationship between temperature and pressure, of course, at a constant volume. So only when the volume does not change, the temperature and pressure seem to have a direct proportionality. So here I have a can of Coke, or an aerosol can, or some sort of spray can with gas inside of it. Constant volume because the can's volume does not change. Well, if I increase the temperature of this can by putting it into flame, what's going to happen to the pressure inside? Obviously the pressure will also increase to the point until, well, the can explodes because the pressure inside is too great. Alright, so this only works at a constant volume though. So the can will explode. If I increase the temperature too much, the pressure inside will get too large. So according to Gay-Lussac's law, the larger the temperature, the greater the pressure, as long as the volume remains constant. As such, temperature and pressure have a direct proportionality, where if one goes up, the other one also goes up. If I cool down the can, so I lower the temperature, well, the pressure should also be lowered as well, so they don't have a direct proportionality. Thus, the equation for Gay-Lussac's law is P initial divided by T initial is equal to P final divided by T final. Or, if you want, P1 over T1 is equal to P2 over T2. Either or is fine. So our next topic is on the Kelvin temperature scale. Here we have a graph describing Charles's law. Notice how as you decrease the temperature of the gas, the volume of the gas also decreases. So what Jacques Charles found was it didn't matter what type of gas he used. So maybe this was oxygen, and he would repeat the experiment with nitrogen and plot it on the graph as well. And same thing with hydrogen and any number of gases. But what was interesting was that Jacques Charles found that it didn't matter what type of gas he was experimenting with, they all seemed to extrapolate and intercept at this one point, minus 273 degrees Celsius. A few years later, an individual named Lord Kelvin comes along, looks at Charles' data, and realizes how important this number is, minus 273 degrees Celsius. You see, as the volume decreases, it gets to zero. Once it reaches zero, it can't go any further. You can't have negative volume. That doesn't make any sense. So the smallest volume of gas you could possibly have is zero. And at this point, that's the temperature, minus 273 degrees Celsius. You cannot get any colder than that. Any colder than that, and you'd be in the negative volumes, which doesn't exist. So Lord Kelvin theorized that at minus 273 degrees Celsius, kinetic energy would be zero. So all molecular motion would stop, and the volume of gas would theoretically be zero. This temperature is known as absolute zero, the coldest you can possibly get. Now it looks like I'm reaching my time limit. Each YouTube video clip can only be 15 minutes long, so I'm going to have to continue this on the next video section.